if you have come to my tutorial, so you know this one, we use it quite intensively. If you ask me, will it be given in the exam? Yes, this one will be given. So hopefully you can use it. Okay. What about that table? Okay, that table is only important when your K is 1.4. And when you have it exactly here. What happens if you have 2.1? You need to do interpolation, right? But the problem when you do interpolation, you do it linearly. Right? You have 2.1, you assume that if this one is 1.4 and 1.5, you get 1.45. In reality, it is not, because it is square root. So, rather than doing interpolation, if I were you, if you do not get exact value here, you better use the equation. Right? Because when you do interpolation, of course, the result will not be precise. Okay, because your interpolation is linear interpolation. Unless you are doing a piecewise linear interpolation. Which means you make it very small, cut, then you do that. But it will take you more time rather than using that one. For me, I will just use that one. It's very simple. Use the P over P star, P naught. Okay, so this one will be given to you if it is needed. And it is applicable for both converging nozzle and converging or diverging nozzle. Any question before we proceed? Okay, so this is a problem example. You have air coming at 400 Kelvin, 100 kilopascal at Mach number 0.3. So if you want to calculate the mass flow rate, right, at the throat when the back pressure is 0.7 and 0.4 megapascal. So first, always calculate the stagnation properties. Why? Because the stagnation properties is the properties that remain constant along the nozzle if you do not have a normal shock. If you have a normal shock, then those properties is not the same anymore. Okay, we will go into it later. So you calculate the T naught and P naught, right? Once you calculate the P naught and T naught, now you can calculate the critical pressure. Okay, if you times this one with the P naught, you get the critical pressure. Now you just compare your critical pressure with the back pressure, right? If PB is more than P star, okay, flow is not, okay, if PB is less than P star, flow is, consequently, when you have this, m dot is not m dot maximum. When you have this, the consequence is m dot is equal to m dot maximum. Yeah. You do that, you calculate. The first one is not choke, so you can calculate it using those. Or if you do not want to remember that because your memory is too precious, if you want to remember fluid mechanics calculation, right? You better remember Korean drama rather than fluid mechanics. So you just remove that and follow this one by one, right? Even during my time, coffee princess is already there. We have this F4.
Yeah, the ozone power.
You know, people better stay home rather than go to Kenduri because of that Taoming. Even my mother. Okay, so if you do not want to remember that, You can do one by one. T, T, rho T, Vt, because m dot is rho T A Vt. Why we don't put star here? Any reason why I don't put star or asterisk there? Why I put rho T A and Vt? Because because the throat is not at a critical condition, so you cannot put star. Star is only for critical condition, which means at the throat when the Mach number is equal to 1. Other than that, you cannot use it. It has to be empty. Empty, not empty. Right? Okay, so the B, you compare it. Now you found that the B is smaller than P star, so the flow is choked. When it is choked, you can calculate your mass flow rate using that one, or you alternatively you can calculate it using this one. The same process. Just calculate one by one, then you will get this. This is the maximum flow rate for the specified nozzle. Okay, any question to this point? Okay, no question. Now, what happens if you have a tire puncture? Okay, actually using the same concept, you can calculate, right? How long it takes. Show me the flow eccentricity. If you take the flow assurance class, this thing is called a pipe blow down. Okay, pipe blow down condition is when you want to release the pressure build up in a pipe. You know, sometimes you have a clogging in a pipeline, because most of the time your oil, the transported oil, is not as liquid as you wish. You know, especially in Malaysia, you have a waxy oil. Waxy oil is the oil that looks like a candle properties. You know, when it is hot, it is liquid. When it is cold, it becomes solid. So it become a, become a solid, and it block the pipe. So how to release that is you release the pressure, right? By releasing the pressure, you make it melt. Okay. So how to do that is you put what they call it, discharge equipment. You puncture it and then you release the gas. So how to calculate the time needed for you to do the operation is using this one. So you calculate it. Okay, you calculate P star of P naught, then you can calculate the mass flow rate, right? Once you calculate the mass flow rate, now after 1 minute, what is the remaining fluid within the pipe, or in this case within the tires, right? If you have the remaining, so initially you got your rho is rho initial times velocity initial, volume initial, right? This is your mass flow rate. Then if you have release for 1 minute, this is 0.554 kilogram per minute, which means after 1 minute you will lose that mass, but the volume remain for the case of pipe, because pipe does not change the shape. Tire of course, but pipe will not change the shape. So the new rho will be m dot initial minus m dot release divided by the volume, because volume is constant. Now you need this one, plug in there, you calculate the V and so on. Then you do iteration. Then you will know how long it takes for you until the gas will reach whatever set pressure. So this is the application of this compressible flow in oil and gas industry. Okay? Yeah? So you can use the same concept as this. You calculate those. You can calculate the mass flow rate. Sorry, yeah. mass flow rate. From mass flow rate, you can calculate the remaining mass inside the tire, and then you can calculate the next flow rate, because it will decrease along the time. Because the pressure is decreasing, of course the mass flow rate will decrease. Okay, so the same like that. This one is only for initial mass flow rate. After some time it will change. Okay. Now if you compare using rho AV and using this, the total, right? You combine everything, you can see that the result is exactly the same. But then I have to highlight here that sometimes you may get slightly different result. Why? Because when you do this, you do one by one, right? You do one by one. This one is most likely not only 2.327. It will be 2.327 to 1067. Depending on whether your calculator is good or not. If it is good, it will give you 100 result there. If not, then surrounding adjustment will be there. Maybe the result will be different. Okay, so don't get worried if your result is not exactly the same with my result. I can still accept it, so long it is steady, right? It will be totally different if I got 2.327 but you got 5.6. Totally wrong. Right? But if you get 2.4, I will look into it. Yeah. Any question before we finish the converging diverging also?